Bismillahirrahmanirrahim. Assalamu alaikum. So today is our fifth lecture of our subject Topological Indices of Chemical Graph. This is 5C. C mean this is our third lecture on graph operations. So this is the contents of our today's lecture: degree-based topological indices and graph operation. And in the last some slides we will discuss some applications of graph operations. So quickly recall the definition of sum or join of graph. G1 and G2 graph are two graphs. Their sum is denoted as G1 plus G2. And the vertex set is denoted by the vertex set of G1 graph union vertex set of G2 graph, and the edge set is the edges of graph G1 and union edges of graph G2 union. Every vertex of G1 is connected with the every vertex of G2. So this is the definition of the join or sum of two graphs. Here we have an example. See, here is G1 and G2. We place G1 graph as it is and then G2 graph as it is, and then connect every vertex of G1 with every vertex of G2. So this is an example of join of graph G1 and G2. If you further notice the formation of the sum of two graphs, you can see that the maximum distance in join graph, the maximum distance is either 1 or either 2. So we discuss this in detail a little bit more. Suppose here we have vertex, these two vertices, the distance between two vertices are 1, you can see. Similarly, you can, if you move into the join, the distance between two vertices is again 1. But this is not always true. Suppose here we have vertex this one like V1, and here we have vertex another vertex V2. You can see the distance between these two vertices is 1, 2 and 3 in G2. But when we in join graph, the distance between these two vertices are always 2, because you can see every vertex V1 is connected with every vertex of G1. So we can move from V1 to any vertex of graph G1 and then to the vertex V2. So observe that the maximum distance in G1 plus G2 is 2. So we have our next result. From the definition of join, the distance between two vertices U and V is either 1 if UV is an edge of G1 or an edge of G2, or the distance between UV is 1 if U belong to graph G1 and V belong to graph G2, or otherwise the distance between two vertices is 2, as we see in our previous example. So this is the result for distance between two vertices in join of graphs. Further, if we talk about the eccentricity of vertex U in join, the eccentricity is 1 if eccentricity of U in G1 is 1, or eccentricity of U is G2 in 1. I mean, if eccentricity in parent graph is 1, then eccentricity will remain same, otherwise the eccentricity will be 2, because we noticed that in the definition that the maximum distance, so the maximum distance in join of graph is 2. So now we will discuss the Wiener index of join of two graphs. Start with the definition of the Wiener index. We see that in the definition we have three types of pairs of vertices. Both vertices are from graph G1, so we partition the summation set. We partition this summation set into 3. Both vertices from graph G1, both vertices from graph G2, and the third one is one vertex is from graph G1 and the second one is from graph G2 spot here. So here is G2. So we partition our vertex set of join graph into 3. Then notice that from this we have G1, because there are edge number of time of pairs, edge number of times of pair whose distance is 1. So total number of pairs in a graph is choose 2. So in a graph there are total number of vertices are order choose 2. So there are EG1 of cardinality EG1, there are pairs which are at distance 1, and rest of the vertices are at distance 2. Similarly, there are EG2 cardinality size time of graph are at distance 1, and the rest of the vertices are at distance 2. This is due to this one. And the third partition gives us this whose those pairs are at distance 1, and the number of those pairs are like order of graph G1 multiply the order of graph G2. So this is just open the summation, apply the summation, and we get this result. And after simplifying this expression last, we get a simplified form of join of two graphs of Wiener index. So this is very simple formula to investigate the Wiener index of join of two graphs, and these two graphs G1 and G2 could be any graph like path, cycle, star, bicyclic, as we said, any two graphs. So next we move to the HyperWinner index, and the lines will be the same, proof will be on the same line. This is the definition of the HyperWinner index. Again we partition into 3 sets. Here, when we talk about the distance, square of the distance plus distance. So, using the definition and this partition, we have our next slide. Like 1/4 is as it is now, because we have distance square plus distance. So we have edge time. We have size time pair of vertices who's giving us term 2, and rest of the pairs giving us here 6. Why 6? Because in formula we have this term 2 square plus 2 is square, this, and these terms are from the second summation, and the last summation gives this. Again some simplification, and we have the formula for HyperWinner index of join of two graphs. Because join is a very friendly for investigating or finding the distances, because every vertex of graph G1 is connected to every vertex of graph 2. That's why we are getting some easy or simplified formula. So next talk about the total eccentricity index of join. The definition of total eccentricity index is given as summation of eccentricities of all vertices of join. This is the definition, and recall that the eccentricity will be 1 or 2. Apply this result into the definition. We observe that there are 2 types of vertices in join: a vertex from graph G1, a vertex from graph G2. Yes. So here N1. What is N1? N1 represents the vertices of eccentricity 1 in G1. Similarly, N2 represent the vertices of eccentricity 1 in graph G2. So the eccentricity vertices with eccentricity 1 represented by N1. Rest of all the vertices have eccentricity 2. And similarly in graph G2, N2 represent the vertices of eccentricity 1, and rest of all the vertices, because this is the total number of vertices in a graph, and rest of all the vertices are of eccentricity 2, and we simplified this expression, and we have the formula of total eccentricity index. So now let's discuss further another topological index, eccentric connectivity index. This is the formula of eccentric connectivity index. degree of a vertex V and multiply the eccentricity of the vertex V. So this is the formula of eccentric connectivity index. We know this formula, and again recall the degree of vertices in join of graphs. If a vertex belong to the graph G1, then its degree is given as degree of V in G1 plus order of G2. If the vertex is in G2, graph G2, then its degree is given by the degree of V in G2 plus order of graph G1. So we will use these to result in our definition to find the eccentric connectivity index. Again, we have two types of vertices here: vertices from G1, vertices from G2. One thing I forgot to mention, that eccentricity of a vertex V is 1 if and only if, suppose G1, degree of V in G1 is n minus 1, where n is the order of the graph G1. So in other words, we can say a vertex has eccentricity 1 if it is connected or adjacent to all other vertices of a graph G. So the degree is n minus 1. So here we notice that n1 is the number of vertices with eccentricity 1, and the degree is given by order minus 1. Next, we have vertices with degree with eccentricity 2. These are the rest of the vertices except n1, and this is the summation of the degrees, which is this one. Similarly, for second graph, n2 into order of graph G2 minus 1 plus order of graph G2 minus n2 into 2 and the summation of graph 2's. Applying this summation, we will obtain a simplified expression for eccentric connectivity index of join of graphs. So we discuss 4 topological indices: Wiener index, HyperWinner index, and total eccentricity index, and eccentric connectivity index for join of two graphs. So next we move to our next graph operation, which is a Cartesian product. Quickly we recall the definition of the Cartesian product. Cartesian product of two graphs is represented by this notation, and the vertex set is given by vertex set of G1 cross vertex set of G2, or in other words, every vertex is in ordered pair form. And two vertices are adjacent if and only if first component are same and second one are adjacent in G2, or first components are adjacent in graph G1 and second components are same. So this is the definition of the Cartesian product, and we have a next result about the eccentricities in Cartesian product. Eccentricity of a vertex UV, because now we are talking about Cartesian product, and in Cartesian product a vertex is labeled as U, V. The eccentricity is given as of UV is eccentricity of U in graph G plus eccentricity of V in graph H. So this is the main formula which we use in our definition to find eccentric related topological indices. So total eccentricity index of the Cartesian product of graph. This is the definition of the eccentric connectivity index. Now we will simplify this expression. As we know by the definition, from the definition of the Cartesian product, that every vertex of graph G must make a ordered pair with graph of H. So we break this summation into two summation. U belong to vertex set of G, V belong to vertex set of G, and we have formula here that eccentricity in Cartesian product is given by this formula. So now we apply this summation to the both terms. Here we have this expression. If you can see that here we have G and here we have G. When we apply this summation on this term, we will get the total eccentricity index, which is this one, and this summation will give this the size of graph H. Similarly, when here we have validated. So mistake, here is H. When this summation is applied on this, we will get the total eccentricity index, and this summation will give, here is G. So this is a very simplified formula of total eccentricity index of Cartesian product. There is an exercise for you. Find the exact formula of the eccentric connectivity index. What you need to do, you need to involve the degree of the vertex V multiply with eccentricity of the vertex V. And from previous lecture, you can find the degree of vertex V in Cartesian product. So let's discuss another graph operation, composition. The composition of two graphs is denoted by this notation. This is also called the lexicographic product. The vertex set of composition is given by vertex set of graph G1 multiply vertex of graph G2. You can say the vertices will be in ordered pair. Two vertices Y1, Y2 is adjacent to Z1 and Z2. There are two conditions. One condition is when first components are adjacent in graph G1, or first component are same and second components are adjacent in graph G2. So this is the definition of composition. You can compare the definition of the Cartesian product and the composition of products. So this is here we have an example suppose this is V1, V2, V3, V1, V2, V3, V1, V2, V3. This is our U1 and U2. So here U1, sorry, this is U2, 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 here U1, U1, U1. So you can see that the first condition is saying that the first component must be an edge. You can see here every edge, this kind of edge is due to the first condition, because first components are making an edge. U1 and U2 is an edge in G1. So this is an edge, there is an edge, there is an edge. The second one is the first component are same. Sorry, first we clear this one, and second you can see that the U1 and U2 again and again. Similarly, all these edges are due to the first condition, and second condition as saying that first component are same. You can see that first component are same here, and the V1 and V2 are edges. So these are the edges due to the second condition. So this is the definition of the composition of two graphs. So we didn't discuss about the eccentricity and the distances in composition of graphs. You should try to investigate the distance formula between two vertices in composition of graph. Also investigate the eccentricity formula of a vertex in composition of graph. After finding distance and eccentricity formulas, you have three exercises. Find the formula of the Wiener index for composition, investigate the formula of an array index for composition of two graphs, and eccentricity and total eccentricity and eccentric connectivity indices of composition of two graphs. So these are three exercises you should try to be good in distance-based topological indices of graph operations. Also, there are many literature available on Google. You can search and explore more result on this topic. So in the last of this topic, let's discuss some applications of graph operations. Why we use graph, why we introduce graph operations, and how we can use this to construct complex networks. So first application is a Hamming graph. Hamming graph is a large graph that can be obtained by Cartesian product of Kni. Kni is a complete graph of order Ni. So Hamming graph can be obtained by applying Cartesian product on complete graph of complete n graphs. Next, C4 nanotube is a molecular structure, is the Cartesian product of path and cycle graph. A special case of C4 nanotube is a prism graph that can be obtained by applying Cartesian product P to Cn. Rectangular grid is obtained by Cartesian product of two paths PQ, Cartesian product PR. Similarly, the square grid will be can be obtained via Cartesian product of PQ and PQ. If we set Q equal to 2, we obtain a famous ladder graph. Similarly, open fence is or can be obtained by composition of Pn with K2. So, in next slide, we have some more applications. Closed fence can be obtained by applying composition C and K2. Complete and partight graph can be obtained by join. Similarly, join can help to obtain the wheel graph. In the graph of the octagonal cobane and truncated hydrocarbon can be obtained by the generalized Eccentric product. So these are very few applications of this graph operation. There are many more graph operations that are used to investigate the properties, structural properties of large and complex networks. And topological indices of complex and networks can be obtained by the formulas which we discuss in our lectures. In the end, we have some references. You can see very latest paper on graph indices and graph operations or graph products. So this is our fifth lecture on fifth C lecture on topological indices. In previous three lectures we discussed our graph operation and topological indices, degree based topological indices and distance based topological indices. In our next lecture we will go switch our topic from computation to extremal graph theory, in which we will discuss some extremal graph with respect to some graph parameter and graph parameter for some topological indices. Then topological indices will be degree based, also distance based topological indices. So if you have some comments or some question, you can discuss in class or you can comment. Okay, then bye. Allah Hafiz.